Assalamualaikum warahmatullahi wabarakatuh, and welcome back, everybody. So this is part 2 of our today's topic, which is a discrete Fourier transform. I assume you guys can hear me. Okay, so
we can hear you, Doctor.
okay, good. Thank you. Okay, in first part, so we have stopped at this point. Okay, so in this example, what we do is we do DFT. We do a discrete Fourier transform, which is this is basically the formula. Okay, and then finally, what we get is our frequency response is a HK equals to 4000, right? So this is our from last part in the first part. And if you want to plot, so you can plot it such this. So which is this is at k equals to 0. This is 1, 2, and 3. And what is this 0, 1, 2, and 3? This is actually frequency. So this is what we call a discrete frequency, right? Because this is a discrete frequency. So it is in integer. So everything is integer. And of course, we can also plot this in terms of omega. So if you want to plot it based on omega, because we have done that. This is actually 0, pi over 2, pi, 3 pi over 2. This is 4. And then 0, 0, 0. Okay, so this is what we have. And you can label it as a h omega, because this is omega. And we are using a square bracket here, because actually we are referring to a discrete frequency, which is we are referring that k in terms of omega. So what we have is just a frequency at 0, pi over 2, pi, and 3 pi over 2. Okay, so this is how we convert. And of course, you can also plot this. You can also plot it on HF. Okay, you just need to convert the value. So what is the formula? So if you want to plot it based on F, so you need to convert that K into F with this equation, which is a K over N. So you will get F. To get omega, you should do this 2 pi K over N. And if you have your frequency sampling, in our example, we doesn't have frequency sampling. So it's not given. So we cannot do this. So you cannot find what is the capital F. So, but if you have your frequency sampling, so you can convert that K into capital F. Okay, because knowing what is the capital N and Fs, so you should, it should be easy to find the capital F. All right, so in this example, n is equals to 4 is similar to the signal length, right? So thus, it is actually enough to represent the frequency response of the signal. And the original signal can be accurately reconstructed. Reconstructed means do inverse DFT, inverse Fourier transform from HK. So from HK, so actually now we can do, what we have done is actually HN to HK, right? So this is actually DFT. And now what we will do is from HK to HN. So this is actually inverse DFT. Okay, so we have seen one example on forward transform. So we will do now inverse transform. And what is the formula? The formula is not much different compared to the forward transform. So if you look here, so what is the difference is only now you have 1 over n at the front. So it doesn't have a 1 over n here, but now you have a 1 over n. And then this negative now becomes positive, right? There's another one here missing. It should be n over there. So 2 pi k n over capital N. So this is positive. This is negative. So that's the difference. One is a sign here, and then we have 1 over n. So the range is starting from 0 up to n minus 1. But this one, the range is supposed to be from minus infinity up to infinity. So whatever you have in your signal in time domain. Right, so let's do that. So from the previous example, so we have this is our HK, which is a 4000. So we want to inverse transform this HK into HN. So then, so this is the generally this is the formula. So Hn is 1 over n summation of k from 0 up to n minus 1, so which is 0 up to 3. And then this is our Hk, then multiplied by e to the power of j to pi k n over capital N over here. And plug in the value, capital N is 4 here, and then n minus 1 is 3. So this is what we have. So this is 1 over 4, 0 up to 3, Hk e j pi k n over 2. Because we already replaced that, the capital N with 4. All right, and then to find H0, because we have n equals to 4, means that the Hn is supposed to have 4 samples also. So n0, 1, 2, and 3. So H0 is plug in this. This is n. Now this is k, right? So previously, what we do is this is n, because we are converting from n to k. So now it is from k to n. So that's why the summation range is for k. Okay. So this is a k from 0 up to 3. So then multiply with hk, you will get 1. So let's try to expand that, because that one is a bit a shortcut. So hk is actually equals to, sorry, not hk. We are trying to find hn from hk. 1 over 4 summation of k. Right. This is not sure why it jumped to that one. This is k from 0 up to 3 of our hk e j 2 pi. So we can remove the 2 already. Pi k n over 2. And this is actually 1 over 4, because this is a, so we will do a h0, 1, 2 up to 3. So h0 of e to the power of 0 plus h1 e to the power of j pi n over 2 plus h2 e j pi n plus h3 e j 3 pi n over 2. Okay, so this is actually the long version after you expand. So you should get something like this, right? And we already know that H0 is 4, H1 is 0, H2 is 0, H3 is 0. So basically what we have is this one will be 0, 0, 0. So then finally you will have only 1 over 4, and H0 is 4. Then e to the power of 0 is 1. Okay? Which is 1. So that is actually Hn. Generally, Hn is equals to 1. So whatever you do here, this is of course for 0 of n up to 3. H0 will be 1, H1 will be 1, H2 will be 1, H3 will be 1. Okay, because even if before you plug in the n value, that 1, so you already have a value. So you have a solution 4/4, which is equals to 1, right? This one. So because in this case, because H1 is 0, H2 is 0, H3 is actually 0 also. So remove everything. So yeah, you can also write it this way. But finally, so this is what we have. Hn equals to 1, 1, 1, 1. So actually this is a proven because originally we have that. So this is our original Hn, so which is a 1, 1, 1, 1. After you do a forward, you get 4, 0, 0, 0. That 4, 0, 0, 0, do inverse, you should get back this signal. Okay. So yes, this is quite a simple example on how to do a forward and then inverse. So let's go to for another example. This is another example. Example 2 is actually another example on inverse transform. Okay. So that's a hint actually. In final exam, there will be inverse transform. So listen carefully. So in this example, so what should we do? What is the question? The question is to find Hn. Find Hn. So what is Hn? Hn is in time domain, which is what we call impulse response. So the time domain impulse response, Hn, of the following frequency response. Okay, so Hk is frequency response. So that one. So then this frequency response is actually referring to a discrete frequency. Okay, because frequency response, you can refer it to physical frequency, you can refer it to that a small omega, the angular frequency of a discrete time signal. You can also refer it to small f, capital omega, but this one is actually referring to a discrete frequency. Okay, because the index is k. And now, so we can write this frequency response in a sequence of values. So if you realize previously in DFT, whenever you get a frequency response, it is in form of an equation. It's not a sequence of value. So it is an equation. The equation sometimes can be a cos something something plus a sine something something. So it is an equation. It's not an absolute value. It's not a sequence of value. So it is represented by an equation because it is actually a continuous value. So a continuous values, you can only represent it using an equation. But because this is discrete, and in this case, so how many samples do we have? So we have only 1, 2, and 3 samples. So whenever you have a discrete values, so you can represent it using a sequence of values, such this, in a vector. So this is what we call, again, a vector. Hn is a vector, Hk is now a vector, right? So if you have H omega, of course, you cannot represent this in a vector form because omega is continuous. So that's the difference, okay? And whenever you have a continuous value, because it is not in vector, so of course, you cannot save it, you cannot store it in your memory. You cannot store it in your RAM, you cannot store it in your ROM. So not possible. So because continuous value, you should have an infinity number of sequence of values. So not possible to be stored. So that's why we do DFT. So we do DFT so that we have a limited number of values of that key. And okay, let's see, this is example. Given is a frequency response, you need to find Hn, which is in time domain. This is in frequency domain, this is in time domain. So what should we do? So we do inverse DFT. Okay, and if you want to plot this, so how are you going to plot this? So because this is actually the original frequency response. So this is to make an analysis, so you need to convert it into magnitude and phase. Right? This is the frequency response. Normally, we don't plot frequency response because it doesn't give us much information. So if you want to plot it, So we need to have a magnitude and phase. Then we can plot it and then do analysis. Okay, but in this example, we don't do, it is not a focus to do an analysis, right? So what we want to do is, we want to do an inverse Fourier transform, inverse DFT specifically. And if you look at this example again, so if you want to do inverse DFT, it must be from frequency response. It's not from a magnitude, it's not from this phase response. Okay, it must be from frequency response. Okay, so if you have in terms of magnitude and phase, you need to convert that into frequency response. Then do the inverse, right? It cannot be from magnitude and phase. Okay, all right. So hopefully that's clear, because we have in frequency domain, we have these things. So we have the original frequency response, and for analysis, we have magnitude and phase. Okay, so do all the calculation based on frequency response. Magnitude and phase is only for analysis. Okay, to find Hn, so let's start. To find Hn, do inverse DFT of Hk, where n equals to 3. So why n equals to 3? Because we have 3 samples here. Okay, so this is 4. You see a comma here, and then this is another comma. So it means that the first frequency response is 4, and then the second one is a minus 0.5 minus j 0.866. The third one is a minus 0.5 plus j 0.866. Okay, so if we are referring to the plot on K, so we have a 0, 1, and 2. But if you want to know what is the omega, okay, so again, what is the omega? Omega is a 2 pi k over n. So what is the n? N is 3. So this is actually 2 pi k over 3. So it means that the first one is, of course, this is a 0. The second one is actually 2 pi over 3. And then this is actually 4 pi over 3. Okay. And just to a more revision on this thing, this is, if we have that one, so this is actually 2 pi. Okay, the last one, because we will stop DFT at 2 pi minus delta omega. So this is actually 2 pi minus delta omega at 4 pi over 3. And this is a 2 pi. If we take half of it, so somewhere here, so this is pi. Okay. And what we know from frequency response, so this is, if this is a part of A, and this is B, so B is actually just conjugate of A. So whatever you have here, this is actually a conjugate value of A. So if you check this one, this is at omega equals to 0. And this is at omega equals to 2 pi over 3. And this is actually omega equals to 4 pi over 3. And somewhere between here is pi. Okay. So this is pi over here. So you have a 2 pi over 3, this one, and then 4 pi over 3. So means that value of this, whatever the value that you have here, this one and this one is actually just a conjugate. This is a conjugate pair. So what is a conjugate pair? So if one value, the sign of the imaginary is opposite. So then you can see that here. So this is the real value is a negative 0.5. The imaginary is a negative j 0.866. And you will have the same value here, negative 0.5, the real part. The real part shouldn't be changed, but you will have a positive sign for the imaginary. This one negative, this one positive, right? So this is if you look at these values, so you know that okay, this is actually a frequency response. So it has all the properties of the frequency response. It is a symmetry. It is a symmetry. It should be. It should be. Okay. All right. So now we know n equals to 3, and then this is the equation for the inverse, which is 1 over n summation of k from 0 up to n minus 1. N minus 1. So because this is a 0, 1, 2, so means that n minus 1 is 2. So now we have this one. 1 over 3 because capital N is equals to 3, and then k is from 0 up to 2, and then hk e j 2 pi k n over 3. So generally we have this because we replace that capital N here. All right. So then we can say that, so this is a h0 expand this. So the first one is a k equals to 0, means that h0 e to the power of 0 because k is 0. So we have this one, h0, plus the next one will be h1 e to the power of j2 pi n over 3 because you replace k equals to 1. Okay, so hopefully everybody can follow because there's a lot of values here. Okay, again, now this one is a k equals to 1 because we need to do k from 0 up to 2. So this is k equals to 0, k equals to 1. Replace that k equals to 1, so you get j2 pi n over 3. This is the last one, which is because we start from 0 up to 2. This is a h2, so e to the power of j. And this is a 2 multiplied by 2. So you get j pi n over 3. So this is what you get. And actually what we can do here is we can manipulate this equation. We can manipulate that one because if we know more on trigonometry, so actually this j4 pi n over 3 is actually equals to minus j2 pi n over 3. So this one will be very helpful because this is a 2 pi over 3. This is minus 2 pi over 3. So the same value, different sign. Okay, so how do we get that? So this is your angular. So let's say this is your, normally we have x and y value, right? So this is 0 degree. This is pi over 2. This is pi. Or you can do this is a 0. This is minus pi over 2. This is minus pi. So this is a 2 pi over 3. So 2 pi over 3 is somewhere there. Okay, so this is a 2 pi over 3. But then, so we have 4 pi over 3. So 4 pi over 3 is, if you divide this region, this quadrant, these two quadrant, 1, 2, 3. So this is another 1, 2, 3. So actually, this is 4 pi over 3. Okay, this one. And 4 pi over 3 is actually, if we do it from here, this is actually just minus 2 pi over 3. So then we will have a good value here because this is the same value, just on a different sign. Okay, so 4 pi over 3, we can change it into minus 2 pi over 3. Okay, so we will see why we do that, because it will make our equation easier and simpler. All right, so this is after expanding it. So we have a 1 over 3 h0 plus h1 e j2 pi n over 3, and then h2 e minus j2 pi n over 3. And if you want to solve it for h0, because we want to find h0, h1, and h2. Okay, because n equals to 3, so we should have a hn for n equals to 0 up to 2. So then plug in the value. This is the n. What is this? This is n equals to 0. Okay. So because in test 2, some of you is having difficulty when trying to find y0. So you do not know what does this mean. Okay, what is actually y0? What is a h0? h0 is actually when n equals to 0. So y0 means you need to find y when n equals to 0. Okay, so that's what it means. So that's what it means, right? This is just it's supposed to be a basic equation. It's supposed to be basic equation, right? This is a function. This is a function. All right. So h0 means n is equals to 0. So when n equals to 0, so what we have here, h0 is we already know h0 is 4. So this is h0 4. So put it there 4, and then h1. So what is a h1? h1 is this one, negative 0.5 minus j 0.866. This one minus 0.5 minus j 0.866. But this one becomes easy because this is e to the power of, then n is 0. Okay, so you can, this one, we can slash this thing because e to the power of 0 is 1. And this one, e to the power of 0 is also 1. So what we will do is just 4 plus this thing, and then plus this thing. So this is what we do. 4 minus 0.5 minus j 0.866 minus 0.5 plus the other one, which is a j 0.866, which is equals to 1 because this is cancelled out, right? Those two cancel out. This is a 4 minus 0.5 minus 0.5 equals to 3. 3 divided by 3 equals to 1. Right? So normally h0 will be very easy, very simple. Okay, now to solve h1, h2, and h3. So this is wrong. Up to h2 only. To solve h1 and h2, it will be easier to write hk in polar form. Okay, because if we do that, because we have this in exponent, so multiplying exponent is easier rather than multiplying a coordinate form. So this is what we call, if you have a complex value, so you can either have it in a form of coordinate form or in polar form. So this is what we call a coordinate form. So it is represented by real and imaginary value. But in polar form, you're going to represent it based on magnitude and phase, right? If you have, let's say, h real plus h imaginary, so this is actually equals to the magnitude of that h to the power of minus j of that h, right? Magnitude and phase. So this is a phase, magnitude, phase. This is coordinate form. Coordinate form. So this one is what we call a polar form. Right, a lot of maths here, especially on trigonometry, complex number. So be careful on that one. So this is the two form of if we have a complex number. So it can be in coordinate form or polar form. But now, so how we do this, so it will be easier. So if we have our hk in polar form. Okay. So the first one is 4. 4 is because we have only a real number, so which is 4. So what is the magnitude of 4? Magnitude of 4 is 4. And what is actually the phase of this one? It will be 0. So then this is e to the power of 0 becomes 1. So that's why we have 4 only. And then the second one. So how to convert that? So you will do that. Find what is the magnitude of this one. And then what is the phase of this one? Okay, so let's see, we have time to do that. 0.5, 0.866. So let's say we have our H1, which is equal to minus 0.5 minus J 0.866. So what is the magnitude? The magnitude will be minus 0.5 square plus minus 0.866 square root. So that's magnitude. Okay, so do that, you should get equals to 1. Okay, so you can try it now. I give you a 10 second, 50 second. So try it. Can you get 1? 0.9999, yes, that's good enough so that we can put it as equals to 1. Then what is the phase? So this is actually tangent inverse of what we call the minus 0.866 divided by minus 0.5. If we look at this one, so you should get minus 2 pi over 3. So can you get that one? Do this. Who can get minus 2 pi over 3? Everyone get this one? So very important here. So someone gets minus 60, 59 degree. So I convert that into radian. Convert that into radian. So can you get minus 2 pi over 3? So who can get minus 2 pi over 3? Are you having problem getting this one? Okay, so actually if you do that, tangent inverse of minus 0.866 divided by 0.5. Let's see, do I have my MATLAB here? Actually, when you do a tangent inverse is a bit tricky. So you have what we call quadrant 1, quadrant 2, quadrant 3, quadrant 4. And tangent inverse is not straightforward. You cannot just do a tangent inverse, divide these two, and then do a tangent inverse, and then you got your answer. So the formula will be a little bit different on Q2 and Q3. So you can do this in Q1 and Q4 only. Okay, so let's do that, tangent inverse. So I think my MATLAB is still opening. But to help that, actually I have written the full equation. I think somewhere at the end of these notes. Not here. Wait. Okay, it doesn't matter. I cannot find it, but it's supposed to be there. Let's get back to our example. Okay, so even in MATLAB, so why is it it takes too long to open? Wait, I got plus 60 actually. My MATLAB is too slow to open. Yes, 60 is actually 60 is what is in radian? Can you convert that in radian?
It's 2 pi over 3.
2 pi over 3.
But it's in positive if I put in calculator. So
Okay. Using calculator, you get H1 equals to 2 pi over 3. So it's not minus 2 pi over 3. So you get a 2 pi over 3. Okay. So, okay, let's see. I'm hoping I can open this one. Right. Okay, so if you do a tangent inverse ETAN, arctangent of, what is the value? The value is minus 0.866 minus 0.866 divided by minus 0.5. And let's convert that in terms of pi. So actually you get 0.3333. Okay, 0.333 is actually 1 over 3. So I'm going to correct that. This is actually pi over 3. Okay, so if you do a calculator, even with this one, so actually what you will get is 1 over 3. So it's not a negative 2 pi over 3. So actually in this one, this is only for Q1 and Q2, Q1 and Q4, Q1 and Q4. So but this one, negative 0.866 and negative 0.5. So where is it? So it's supposed to be 0.866 is somewhere here. Let's say here. And then the other one is minus 0.5, let's say here. So it is somewhere here. This is in quadrant 3. This is not in quadrant 1. This is not in quadrant 4. So it is on a quadrant, on quadrant 3. So in quadrant 3, so what you should do is actually whatever you have, which is a pi over 3, so you need to minus with pi. This one, you need to plus with pi. Okay? So because if you get a pi over 3 is not on quadrant 3. Pi over 3 is somewhere here. Pi over 3 is on quadrant 1. So whatever you do, if you do using your calculator, doing a tangent inverse, so you will get somewhere in quadrant 1 and quadrant 4 only. So you will not get anything from quadrant 2 and quadrant 3. So but because we know that this is a negative 0.866 and this is negative 0.5, it's supposed to be on quadrant 3. So to correct this thing, so you need to minus with pi. So then over here, so what we have here is pi over 3, then you should minus with pi. So this is where something like a pi minus 3 pi. Sorry, not over pi, over 3. then you have your 2 pi over 3. Okay, then it is corrected because 2 pi over 3, yes, it is on quadrant 3. Because this is pi over 3. This is 2 pi over 3 here, positive. This is pi over 3. Somewhere here is negative pi over 3. And then somewhere here, it is negative 2 pi over 3. Okay, so you need to be careful on that one. So we need to know our point, it is in which quadrant. So if it is in quadrant 1 and quadrant 4, you doesn't need to do any correction. So, but if it is in quadrant 2 and quadrant 3, you need to do some correction, which is in quadrant 2, you plus with pi. In quadrant 3, you should minus with pi. So then this is what we get, minus 2 pi over 3. And if you look at our next point, so which is negative 0.5 plus 0.866. So this is where it is in quadrant 2 over here. Because it is now on positive 0.866 somewhere here. So which is, this is in quadrant 2. So when you do a tangent inverse, you will get negative pi over 3. So that negative pi over 3, then you need to plus with pi. Okay, negative pi over 3 plus with pi, so you will get 2 pi over 3. So this is what you will get. All right, so that's some trick on doing a tangent inverse because it will not be straightforward. And in MATLAB, so if you want to have a full calculation on the 4 quadrant, so you don't use ATAN. So you're supposed to use ATAN2. This one, do not use ATAN alone. Okay, you need to use this version, ATAN2, because it will do a 4 quadrant inverse tangent. So if you are ATAN, so then what is the 4 on the 2 quadrant, the first quadrant and the 4th quadrant, not the whole quadrant. All right, so enough for the maths revision, a lot of maths. So, but hopefully it make things easier. It make things easier because we need to solve this thing. We need to solve it. So now, okay, now we have a HK equals to 4. The magnitude is 1 for the second point, second frequency here. So this is E minus J2 pi over 3, and then this is E J2 pi over 3, right? Our frequency response in polar form. So then, go back to our, what is our formula again? So Hn is actually 1 over 3 H0 plus H1 multiply with E J2 pi n over 3. And then plus again another one with H2 e to the power of minus J2 pi n over 3. Right? So remember this one. So we need to multiply with 2 pi n over 3. So then, so this is where now we have the first one is easy because it's just 4. So we just take that 4. So the second one we need to multiply with J2 pi over 3. And then what is the H1? H1 is minus E minus J2 pi over 3. So we put it here. And then the second one. So this is negative, this is positive. So now we have a positive here. Then this is becomes very, very easy because minus J2 pi over 3 multiply with E to the power of J2 pi over 3. So you will cancel out these two. Okay, because you need to plus these two. So the same thing, plus becomes 0. So E to the power of 0. Again, this thing, same thing. So then what we will have is 4 plus 1 plus 1. So which is 6, and then divide by 3 equals to 2. Okay, that one is a H1. Second one, H2. So which is the last one. So this is the last one, H2. So what is a H2? So 1 over 3, 4 plus, so this is the same thing, J2 pi over 3. And now, because we need to multiply, now we have the n value here. So when n is equals to 2, so this one becomes 4. When n equals to 2, this one The same thing becomes 4. Okay, so that's why we have 4 here. So minus j2 pi over 3, and then you multiply by j4 pi over 3, and then this is j2 pi over 3. The same thing here. This is minus j4 pi over 3, and then do the summation. Minus 2 pi plus 4 pi, so you get 2 pi over 3. And this is 2 pi over 3 minus 4 pi over 3. So 2 minus 4, you get minus 2. Right? So 1 over 3, 4 plus e j2 pi over 3 plus e minus j2 pi over 3. This is also easy to solve because this is the same. 2 pi over 3 minus 2 pi over 3. So it becomes 2 cos 2 pi over 3. Okay, this is this one. It becomes the 2 cos 2 pi over 3. Then solve that 2 cos 2 pi over 3. This is where you will get equals to 1, 2, okay, and then 0.5. This one becomes a 0.5 multiplied by no, maybe I'm wrong. Supposed to solve that, okay, and then it's supposed to, I think, minus 0.5. Okay, this one supposed to be 0.5. 0.5 multiplied by 2 minus 1, so 4 minus 1 is 3. So 3 divided by 3, you will get 1. Okay, so that's how you solve it. Solve this thing. Okay, when it is in polar form, so it becomes easier to solve. It's just that you need to be careful because converting it into a phase, you need to consider this 4 quadrant. So if not, your value will be wrong. All right. So we have finally Hn equals to 1, 2, and 1 because this is the last one. H2 is equals to 1, H1 equals to 2, and previously, so we have done that. H0 equals to 1. So that is so this is our final answer. So what is this? This is impulse response. So from a frequency response, so we do inverse DFT to get our impulse response. Because in this case, we are dealing with the impulse response. Okay, it can be also on signal. So if you are given xk, so when do inverse, so you should get xn, and xn is a signal. Normally, it is an input signal, right? So that one is not called impulse response. Impulse response is only for Hn. Okay, all right. So we have finished today looking at 2 examples. So which is one, doing a forward. Basically, the first example is on forward transform, and then another example on this second part is on inverse transform of this DFT. So we can do that. We can do the inverse because everything now is discrete. Because because when it is discrete, so the formula becomes a summation. So if you realize previously in DTFT, we don't really do inverse. Okay, so if you do inverse, you will convert that into a Z transform first, the system function, and then referring to table, and then you do the inverse Z transform. Okay, by referring to table. So we don't really do this equation because the equation is actually integration. So in discrete, we don't like to do integration. The summation is good because summation is very easy compared to integration. So because we have done that integration in previous courses in signal and system and control system in a circuit theory. So you have a lot of integration previously. So we're not going to do that anymore. Okay, so any questions? So we have finished next Thursday. Next Thursday, we're going to look at another example. Okay, so we have another example, more example. So this is example 3. We have actually another 2 example. So hopefully I can finish the 2 examples. So if the time is not very limited, maybe I'm going to pick one of the example, okay, in class. So or maybe I'm going to continue in the next week. Right. So any questions before we stop? So I assume there is no questions. So okay, just a reminder, please do your assignment. And of course, this is a very busy week. You will have your capstone next week, but you need to submit everything by 15. And then after capstone, you will have your FYP presentation also. Okay, so please plan everything so that you can do everything, because this is a part of your study in this semester. Okay, so that's all for today. So see you guys again next Thursday.
Thank you, Doctor.
Welcome.